Okay, so here we'll talk about solenoid. Okay, in Chinese just 线圈. Okay, so yeah, so here we try to mention this structure will try to generate some B field. Okay, actually the B field are not that simple. Okay, so you can see the B field line as something like this one, and then here with some fringing, and also here yeah, another pattern. Roughly there are three patterns. Okay, one of it is this one, and then this one rotating around the wire, and then also we have this one. Actually this just like yeah, roughly like a magnetic dipole, but yeah, more a little bit more complicated than that because we have multiple wire. Okay, so here for the solenoid, it's just like we have a current going in this way, okay, until going out from here. Okay, so all the way the current will be I. But if we have more turns, okay, 比较多圈, okay, more turns or more windings. Turns, sometimes we call it turns or sometimes we call it windings. Okay, that make up the solenoid. Okay, if we have more turns, then the B field generated by the solenoid will be stronger. Okay, so for points very close to a turn, the wire behaves magnetically almost like the long straight wire, and the line B there are almost concentric circle. Okay, so this is the first case. This is the first case, which means that this one are the first case. Okay, so which means that if you try to zoom in, although this is like a turn, okay, this is not a long straight wire, but if we really go very close to it, then it feels like it is very long. So the idea is like this. Okay, so if we try to find a region close to this wire, then here the B field line will be like concentric circle around this wire. Of course, yeah, for this point it is in this surface, this is like this, and then for this point this is here, then the B field line will be like this. Okay. So this is in a 3D three-dimension case. So yeah, so try to consider the direction of it carefully. Okay, so yeah, so of course it is actually follow the right hand rule. Okay, so here you can see a cross, which means that it is into the page. So using the right hand rule, your thumb pointing into the page, so the green line, which means the B field line around it, is like clockwise. Okay, so this sign is the other way around, because it feels like it is pointing into the page and then going to here, going out of the page, and then to the next loop. Okay, so although it is not explicitly drawn out, so it should be something like going from here and then going into the page to here, going out and then going to the next loop, something like this. Okay, something like this to form the whole loop. Okay, but it doesn't try to draw it out because the figure is already quite messy. So if we also try to draw that part, then okay, if it is even messy, then you have no way to understand. Okay, so for that part, this is pointing out of the page. So using the right hand rule, it is counterclockwise. So this is the first. This is also the first pattern. Okay, so for the second pattern, the field tends to cancel between adjacent turns. Okay, which means that it mentioned the part around here. Okay, so for there, it try to cancel. Okay, because you can see for this part and this part. Okay, here this is clockwise. This is also clockwise. So going to that part, right in the middle of two turns. Okay, one is it the pointing one of it is pointing downward, one of it is pointing upward. Okay, so they perfectly cancel. Okay, so for the third part, at points inside the solenoid and reasonably far away from the wire, B is approximately parallel to the central. Okay, for the third part, it really means that I use another color. Okay, which means this part. Orange is not good because it is the same color. Yeah, maybe I use the pink. Okay, this is the third part. This is yeah, this is the third pattern. Okay, here. So this is in the middle, and far away from the wire, which means that really inside it. Okay, so we will assume that the B field is uniform and then pointing to the right side. Right. We also use the right hand rule to determine. You use the forefinger, follow the direction of the current. Okay, so this is into the page. This is out. Okay, so the direction is something like this. Okay, your forefinger following the direction of here. Your thumb is pointing to the right side. Okay, so so still using right hand rule all the ways to determine the direction of the B field or whatever. Okay, so yeah, so in the middle part, okay, it is uniform, but outside is become weaker. Okay, and then become a dipole, and then it will just looping like this, like a dipole. Okay, so but actually this is the practical this is the real case, but this is too difficult to mention. So later we will do some approximation. It means that here we try to consider a solenoid. This is just a cross section. We try to cut it like this, and then so we can just see this is just a cross section diagram, and then all these current are going out of the page. All these current are going in the page. Okay, so the current is actually like this. Okay, like this, turn after another. Okay, so here the approximation is like we assume that B is uniform within the solenoid. B is uniform within or inside the solenoid, and 0 outside it. Okay, so we just ignore all this case, and then we just assume that for the whole area, the B is uniformly pointing to the right side, and then this is the approximation. Okay, so using the Ampere's law, okay, we try to calculate the B field. What is the B field? Okay, so here, different from the previous case, we don't try to assume a circle Ampere loop. Here we assume the Ampere loop is a rectangle like this. It's a rectangle like this. So these two sides are parallel to the axis of the solenoid. Okay, so this side is inside the solenoid. So it has B field. And this side is outside the solenoid, so no B field there. And then for these two sides, it is perpendicular to the B field. Okay, so B dot ds won't contribute. Okay, so for this side, B dot ds is 0 because B and ds are perpendicular to each other. Okay, so this is ds here. This is ds. Okay, and then this is ds. But here for this part, B is 0 outside. So 1, 2, 3 from BA. Okay, so let's see. This is the Ampere's law. Integration of B dot ds equals mu 0 I enclosed. Okay, so this is a line integral from A to B to C to D back to A. Okay, for the complete rectangle. Okay, so which means that we can draw it as line integral from A to B, B to C, C to D, D to A. Okay, so just add these 4 together to become the whole line integral. Okay, so just as what I mentioned, from B to C, C to D, D to A. they are just 0. Okay, so this one is 0, this one is also 0, this one is also 0. Okay, so the only remaining term is this one. Okay, this one. Great. So so we only need to find b dot ds from a to b, from a to b. Hopefully b is parallel. B is parallel to ds. ds is pointing to the right side. B is also pointing to the right side. B and ds are parallel, which means that b dot ds is nothing but b times ds. B times ds. Just write like this. B times ds. And then b is also uniform. Okay, so we can just put it outside. Put it outside the integral side. So it becomes b times integration of ds from a to b, which means that it is nothing but the length from a to b. Here we just assume that the width of the rectangle is h. So this is b times h, as what we have right here. Okay, so for the left side of the Ampere's law, we have bh plus 0 plus 0 plus 0. Okay, so it is nothing but b times h. Okay, so this one becomes bh equals mu 0 I enclosed. I enclosed, we need to determine what is I enclosed. For every dot, it is I. For every dot, it is I. So how many I there? How many I there? Okay, we only know the width is h. The width is h. So we need to introduce another term called the number of turn per unit length. Okay, so here n is the number of turn per unit length. Okay, so be careful. I have already mentioned that in these 2 or 3 chapters, we sometimes have capital N, means number of turns. Number of turns. So it just try to count 1, 2, 3, or 4. Okay, so on and so forth. But here it is number of turn per unit length, which means that we try to count how many turns per 1 meter. Per 1 meter. Okay, so this small n means the turn density of the turn or number of turn per unit length. Okay, capital N directly means number of turns. Okay, so be careful. Okay, so as much as we have number of turn per unit length, and then we multiply it by h, so it becomes the number of turn within this rectangle. So the number of turn here will be n times h, times I. Okay, this is how many I. Okay, times number of times the I. So this is the total current enclosed by this Ampere loop. Okay, a little bit tricky because we introduce a variable n here. Okay, so finally we can just cancel h on both sides. So it turns out to be b equals mu 0 ni, or b equals mu 0 in. Okay, so this is the final expression for the B field inside the solenoid. Okay, we assume that the B field is uniformly inside, and then this B, okay, equals to mu 0 in. Mu 0 is a constant, 4 pi times 10 to the negative 7th. Okay, I, so it's proportional to I, and also proportional to the number of turn per unit length. Okay, if we can pack more number of turn in a unit length, then the B will be stronger. And then, or if we cannot pack more coil, then we can just increase the I. Okay, so it's just like a B is proportional to I. Okay, so in chapter 30, we will just call this one an inductor. Okay, inductor. Yeah, I don't think there are any difference between them. So yeah, but in chapter 30, we will just call it inductor. 中文叫做电感。电感。 Okay. Yeah, so we have another thing called the toroid. Just now we have the solenoid. Okay, so this one is called toroid. Okay, so this one is the toroid. Is described as a hollow 空心的 solenoid, hollow solenoid that has been curved until its two ends meet. Okay, so at the very beginning you have a solenoid and then you try to bend. Okay, at the very beginning you have a solenoid. Okay, but of course this should be longer, and then you try to make this one touching. The two ends touch each other. Okay, so it form a toroid. Okay, it's form a sort of hollow braces. Okay, it's just like a 手链 bracelet 手链. Okay, so from the symmetry we can see that the line B form a concentric circle inside the toroid. Okay, so yeah, so this is the cross section of the toroid. Okay, you try to cut this like this. Okay, cut this like this. So this is the cross section diagram. Okay, so of course, yeah, so these current are going into the page. These current are going out of the page. Here we try to assume the ambient loop to be here. So all these circles are concentric. Okay, and then of course we can just simply assume that yeah, this is clockwise. The direction of the ambient loop is clockwise. Okay, so and also the radius of this ambient loop is small r. So on the left side, okay, of course it is from integration of b dot ds equals mu 0 I enclosed. Okay, so on the left side, as always, it is b times 2 pi r, and then on the right side mu 0 I enclosed. So here we have mu 0 I capital N. Okay, so be careful, this is capital N, means the total number of turns, because for this ambient loop the enclosed current only includes all this, only include this. Okay, so this is the total number of turns. We don't need to count or how long it is. Okay, so this is how many n here. N times I is the total current enclosed by this ambient loop. Okay, and of course it is pointing into the page. All of them are pointing into the page. Okay, so here we have b equals 2 pi r. B times 2 pi r equals mu 0 I n. Okay, so this is I enclosed. Okay, so finally b equals this term over 2 pi r. So nothing special. Yeah. But here, inside the toroid, the B field is not uniform. Because B is related to R. So the B field is stronger for a smaller radius, and then B is weaker for a larger radius. But still, we just assume the B field is 0 outside the toroid. Okay, so in contrast to situation for solenoid, B is not constant over the cross-section of the toroid. Okay, so here we have a sample problem. So it says a solenoid has length L and the inner diameter D. It carries a current I. It consists of 5 close-packed layers, each with 850 turns along the length. What is B at its center? Okay, so as much as this is a solenoid, okay, we can just use B equals mu 0 I small n. Okay, small n. Okay, so mu 0 is nothing but 4 pi times 10 to negative 7, and then times I is this one, 5.57. Okay, so here we need to determine what is n. Okay, so this is the total length. So probably we need to divide this L so that it becomes a number of turns per unit length. Okay, so here we try to find how many turns there. Okay, the turns is like there are five closed pack, and then each pack will have 850. So which means that the total number of turns will be 5 times 850, and then divided by L. L is a 1.23 meter. Okay, so this number is not necessary here. Okay, so the final answer is 2.42 times 10 to negative second Tesla. Okay, so this sample problem is pretty easy. We just need to use B equals mu 0 I n. Okay, so next here we talk about the current carrying coil as a magnetic dipole. Of course, we have learned something called electric dipole before. Okay, actually, for the electric dipole and the magnetic dipole, yeah, the B field line generated by the magnetic dipole and the E field line generated by the electric dipole are actually the same, with the same shape. Okay, although how to generate the electric dipole and magnetic dipole are different. For the electric dipole, if you still remember, electric dipole is like two charges, one positive Q and then one negative Q are placed close together, and then this distance is d. And then the magnetic dipole, the electric dipole moment is nothing but Q times d. Or make it like a vector. Oh, okay, this d is from the negative charge to the positive charge. Okay, so this is the electric dipole moment. So here for the magnetic dipole moment, it is just like a current loop. Okay, if it is a wire and then with some current, okay, so this will become a magnetic dipole. So this wire with the current is equivalent to the magnetic bar. Okay, so for this graph, it doesn't mean that we have both this wire with current and the magnetic bar simultaneously. It means that this one and the magnetic bar are equivalent to each other. If we have this one, we can generate the B field line like this. If we don't have the magnetic bar but with the wire, it will also generate the magnetic field line like this. You only need to adjust the current I so that they can actually generate exactly the same B field in the space. Okay. To change the I, it will just change the magnitude only. Okay, linearly. Okay, so here it just mentioned that if we have a magnetic dipole, it may be a current carrying loop or a magnetic bar. Okay. So the expression is like mu 0 over 2 pi times mu over z cube. Okay, later we will show how to derive this one out. Okay. Also, here z is the axis here. This is z axis. Okay, so this is the current carrying loop. We assume it to be a circle. So this axis is going through the center of this circle and then perpendicular to this plane. Okay, and then this is the z-axis. Okay, so this expression only consider the point along this z-axis. For other points, the expression are not so elegant, so we only have this expression. And then also we consider z is much greater than the dimension of the coil. So for the far field condition, if you still remember, we always consider the far field condition. For that time, it just means that z is much larger than d for the electric dipole moment. For here, for example, this is the radius r. We also consider z is much larger than the r. Okay, if it is close to it, then this expression might not be so correct. And then before we try to derive this expression, we try to recall for the electric dipole. Oh, this is P rather than mu. Last time I forgot what is the variable for the electric dipole moment. Okay, so for the electric dipole moment, it is P. Okay, so here you can see, okay, so in chapter 22, we already derived this one out. Okay, so here we try to, let's say, we try to cancel this 2 and this 4. Okay, so it shrink down to E to be 1 over 2 pi epsilon naught times QD and then over CQ. Okay, so this QD is the electric dipole moment. So it is 1 over 2 pi epsilon naught and then P over CQ. Okay, so just as what I mentioned, there are some duality there. So which means that for this one, you just change E to B. And then 2 pi doesn't need to change. So we have 2 pi. And then for this epsilon, you change it to 1 over mu naught. And then for P, you change it to mu. Okay, so from the electric dipole to magnetic dipole moment. Electric dipole moment to magnetic dipole moment. And then C cube doesn't need to change. Okay, so just do this conversion, then you will see this mu naught go to the bottom. It becomes mu naught over 2 pi. So you can see mu naught over 2 pi and then mu over C cube. Okay, you can get this one without calculating. Yeah, but of course we need to do it rigorously. So here, okay. Okay, so before mentioning the derivation of the equation, here we see that a current carrying wire as a magnetic dipole. Okay, so it says we have two ways in which we can regard a current carrying coil as a magnetic dipole. Okay, the first one is it experiences a torque when we place it in an external magnetic field. Okay, so if we just place this one in the external B field, this external B field shaded with a green line, which is generated by this big magnet bar. Okay, so this is the north pole, this is the big south pole. Okay, so it will generate a B field pointing to the right side uniformly. Okay, if we just place a coil, current carrying coil here, and then with a rotational axis, it will try to rotate. Okay, we just mentioned it in the last lecture. Okay, so you will see the torque. The torque will be like mu cross B. Yeah, if you still remember. Yeah, so this is the first one. And then the second one, it generates its own intrinsic magnetic field given for a distance point along its axis. Okay, so this one, I mean the magnet bar will generate the B field line like this. Or if we just remove or replace the magnet bar by this current carrying coil, it will generate the same B field line pattern. Actually the same thing by adjusting the I. Okay, all the things will be the same. Okay, so you can regard this one and this one are equivalent to each other. 它们是等效的. Okay, so here we try to derive this equation using the Biot-Savart law. Here we cannot use the Ampere's law. But hopefully this is not too difficult. Okay, so here is the current coil, but in a special angle, we can just see a line. But actually, this is a coil. This is a coil. Okay, so this coil, at this point, this is pointing out of the page. This is into the page. So this is a circle like this. Okay, going out of the page and then going in. Okay, going like this. Okay, going like this. Okay, so here, this ds is pointing out of the page, and then we consider the point P here along the z-axis, okay, which means that we try to connect this point with point P. Okay, so this is our axis for this ds. Okay, so ds pointing out of the page, r is pointing to the top right. R is pointing to the top right. So using right hand rule, like this. Okay, and then you cross it to our head. Okay, so db pointing to the top left. Okay, and then this db we can decompose it along the z-axis and along the xy plane. Okay, so we have a db parallel, which is the db along the z-axis, and then db parallel, db perpendicular is along the xy plane. Okay, so also we can see that this is ds. ds is pointing into the page, and then for this one, r is in this direction. So this is dr for this ds. Okay, using right hand rule, okay, ds cross to r. So db points to that side. db points to that side. Okay, so db points to that side. Okay, so db points to that side. db. Okay, so you can see that db parallel, they will point to the same direction, but db perpendicular, these two db perpendicular will cancel each other, which means that we only need to consider db parallel. So here we write it as db equals integration of db parallel. Okay, so here we start from the Biot-Savart law. db equals mu 0 over 4 pi I ds cross r hat over r squared. And then db parallel is actually this one, and then times the angle alpha. Yeah, let me just erase this one. Okay, the alpha is this db. Okay, this db will have an angle between the z-axis, because we try to project this db to the z-axis. Okay, so this one db parallel will be db times cosine of alpha, because this is adjacent side. Okay, adjacent side over this one will be cosine of alpha. So we have cosine of alpha here. ds and r hat are perpendicular to each other. So for this cross product, it is nothing but ds times 1. So this one becomes ds. This comes ds only times 1, which is ds. Okay, so we have ds cosine alpha mu 0 I and then 4 pi r square here, like this. Okay, so we can just plug in this expression to here, and then also we need to do some substitution, because we will integrate over ds from 0 to 2 pi r. Okay, this is the integration variable, so we need to express all the other variable in terms of that. Okay, so actually r is from this point to there, so this is small r. Small r is an unknown value actually. So we need to express it in terms of z and capital R. Capital R are known because this is the radius of the current loop, and then z is the direction from this loop to the point P we concern. Okay, so these two variables are unknown values. Okay, so R is square root of capital R squared plus z squared. Okay, then we can plug it in here. And then for cosine alpha. Okay, cosine alpha. Okay, so this is alpha. And then this is right angle. So this one will be pi over 2 minus alpha. This is pi over 2 minus alpha. And this is another right angle triangle. Okay, so this one is also alpha. Okay, so this is alpha, which means that cosine alpha will be capital R over small r. So cosine alpha will be capital R over square root of capital R squared plus c squared. Okay, we can also plug in this one to here. And then all these terms are constant, so we don't need to care. So dB parallel will be mu 0 I over 4 pi, and then ds we just put it there, and then cosine alpha will be r over this one, and then r will be this one square. So altogether we will have this term to the 3 over 2 power, and then also we have this r in the numerator. Okay, so this is dB parallel, and then finally we can really plug in this one to here, and then we can do the integration. But this integration is really easy because all these terms are just constant to ds, so we can just put all the things out of the integration sign. So integration of ds is nothing but the circumference of the loop, so which is just a circumference of a circle. So this one is nothing but 2 pi r. So this is 2 pi r. So 2 pi and 4 pi will be partly cancelled, becomes a 2. And then r will become r squared. Okay, so B is having this expression. And similarly, we also apply the far field condition. Which means that Z is much larger than R. Which means that this R can be ignored. Okay, in this case, this R can be ignored because Z is much larger than R. So in that case, in this term, R squared can be ignored. So it becomes C squared to the 3 over 2 power becomes C cubed. So all the other things remain the same. So mu 0 I over 2 here, and then R squared still there, and then here this whole term becomes C cubed due to this far field condition. And then finally we try to form the magnetic dipole moment, because last time we already know mu is n, number of turn. Of course here we just draw one turn there, but actually we can have more than one turn, so we can keep this n here, and I, and also a is nothing but pi r square. Okay, so we try to form this thing out. Here we don't have this one explicitly, so and then we also assume that n is 1. So yeah, n is 1. So we just ignore n here, but of course we can just put more turns. Okay, so here we try to multiply pi and in the numerator and denominator, okay, together, so that they will cancel. But yeah, here pi r squared will become a. Okay, so it becomes mu 0 ia, and in the denominator 2 pi z cubed. Okay, so this ia, we already mentioned that n is 1, so yeah, so ia is already mu, so we have a mu 0 mu. Okay, of course these two mu are different. This is the permeability constant, this is the magnetic dipole moment. This is the permeability constant. Okay, so although they are mu, but this is mu naught, this is mu. Okay, but they are different things. This is permeability constant. This is magnetic dipole moment. Okay. Okay, so finally we get this expression. Okay, and yeah, so at the end we have two additional examples. Okay, so let us finish it quickly. So first one is the two circular arcs have radii A and B, subtend angle theta, carrying current I, and share a same center of curvature P. Okay, so these two curvature share the same center. Okay, what are the magnitude and direction into out of the page of the net magnetic field at P? Okay. Okay, so first of all, this shape has four segments. Okay, 1, 2, 3, 4. Okay, so let's call it 1, 2, 3, 4. Okay, so we can clearly see that the segment 1 and segment 3 will not contribute B field at point P, because you can consider the Biot-Savart law. Okay, ds is here, and then R hat points to the same direction, so ds cross R hat will be 0. Similar for this one, ds is pointing to this direction, R hat points to the opposite direction. They have a 180-degree angle between them, so the cross product of them will be 0 either. So only this segment, this one and this one, this is the direction of I. Okay, these two segments will contribute B field at point P. Okay, so B field will be mu0 I theta over 4 pi B. Okay, B is this one, A is this one. Okay, so you can consider this term is larger, and then minus mu0 I theta 4 pi A. Why one is positive, why one is negative? Because using the right hand rule, okay, you use your forefinger, follow this direction, your thumb will be pointing out of the page. Okay, will be pointing out of the page due to segment 2. Okay, and then using the right hand rule for segment 4, okay, your finger follow the direction of current, and then your thumb pointing into the page. Okay, so they are pointing to the opposite direction, so one is positive, one is negative. Okay, and then you can clearly see that B is smaller to make this term larger. Okay, so this is positive, this is negative, and then we can determine that the total B field at point P will be pointing out of the page. Okay, so finally, B, for part B, it is out of the page. For part A, we calculate the magnitude. Okay, so we just need to plug in the number mu0 I theta over 4 pi, and then 1 over B minus 1 over A. And then we just plug in all the value. Mu0 over 4 pi, for this whole thing, it is 10 to negative 7. And then times I is this one, 0.411, and then times this one. We actually need to use the radian, so we need to 74 degree over 180 degree, and then it is pi radian. Okay, so this is how to convert the angle between degree and radian. And then 1 over B is 10.7, 0.107 meter, minus 1 over 0.135. Okay, so this number is 1.02 times 10 to negative 7 Tesla. Okay, so this is the B field generated by this structure. Okay, so this is not that difficult, just need to add two terms together. Okay, so this is the final additional example for this chapter. Okay, so here it says a long circular pipe with outside radius R. So this is the outside radius R from here to there. Okay, this is R. Okay, carries uniform distributed current I into the page. Okay, so it denotes by some cross here. And then a wire runs parallel to the pipe. Okay, this is the wire at distance 3R. So you can see 1R, 2R, 3R. So this is the wire. From center to center, find the magnitude and direction of this current. Okay, you need to determine what is I here, and whether it is going into the page or out of the page for question A and B. And then it makes, let me see. So such that the net magnetic field at point P is here, has the same magnitude as the net magnetic field at the center. Okay, so this one we call it center. Okay, these 2 points have the same magnitude of B field, but they are pointing to the opposite direction. Okay, So these 2 points have same magnitude but point to opposite direction. Okay, so first, let me see. So let me consider the B field at here first. Okay. So for BC, which means the B field at the center of this pipe. Okay. This one won't contribute to here because you can simply consider the Ampere's law. You can just assume, assume the Ampere's loop like this. It encloses nothing, and then you try to decrease the radius of this Ampere's loop until 0. Then it shouldn't enclose nothing, and then this is symmetrical structure, so it will not contribute B field here by this structure. Only the wire will contribute. Okay, so here we just try to assume that IW is I'm not sure whether it is into or left. So you just assume this is IW rather than I. So BC will be mu0 times IW over 2 pi, and then the distance from here to here is 3R. So 3R, and then plus 0. 0 is from here. 0 is from here. Okay, so this is mu0 IW over 6 pi R. And then for BP is here. Okay, for this pipe, this is 2R. So actually this is mu0 I is of this one, okay, over 2 pi times 2R. 2 pi times 2R. Okay, so the B field generated by this one, and then also this one. Okay, minus mu0 IW over 2 pi. Okay, the distance here is only R. Okay, so here it means that we assume that IW is out of the page. If we calculate a negative result, then it is into the page. But here we just assume that IW is out of the page. Okay, so here, this is the magnitude of BC, and then this is the magnitude of BP. And they have the same magnitude but opposite direction, which means that BC equals to negative BP. BC equal to negative BP. Then we will have mu0 IW over 6 pi R equals negative sign, so it becomes mu0 IW over 2 pi R, and then minus mu0 I over 4 pi R. Then we can do some cancellation. We just move this one to here. Okay, then these two terms can combine, and then we move this term to the left side. So we will have mu0 I over 4 pi R, and then this one mu0 IW over 1/2 minus 1/6. It becomes 3 over 4 minus 1. Sorry, I mean 3 over 6 over 3 minus over 1 over 6, and minus 1 over 6, which is 2 over 6, which is 1/3. Let me see. Yeah, it is actually 1 and 2/3. Let me see. IW minus. Wait. R's. Sorry, this one should be IW. This one should be I. This one should be I. So this one is I. This one is IW. Sorry. This one is IW. Okay. So it should be like It should be like we try to move this one here. Okay. So yeah, so sorry. So it should be mu0 IW over pi R. Okay, so this one, 1/4 plus 1/6. 1/4. No. Let me see. This is sorry, this is R. This is 2R. This is 2R. So let me see. So this is 2. This is 4. This is 2. This is 4. Okay, it should be like that. Okay, so it should be 1/2 plus 1/6. So it becomes 2 over 3, and then equals mu0 I over 4 pi R. Then we can do all the cancellation. Okay, so we can cancel this mu0, and then pi R. Okay, so finally we will get IW equals I times 1/4 times 3 over 2. Okay, which means this is 3I over 8. Okay, so here we have I equals to 8 MA. So this is 3 MA. Sorry, 3 MA. So this is the answer of question A. Okay, so actually, if we write it like this, this is pointing into the page. This is pointing into the page. This is pointing into the page. So for part B, IW is pointing into the page. Into the page. Okay. So you can try to verify it at your home if you have interest. Okay. So